Hello again. Thank you for joining us. This is Space Nuts, where we talk about all sorts of astronomical and space science things. And coming up on today's show, we're going to get some more information from Ryugu, the asteroid that they took some samples from about four years ago. It's back in the news because, we talked about it a few weeks ago, and now we're looking at maybe the origins of our outer solar system. Some new information on what really happened to the Arecibo Observatory, and it's a bit of a sad tale. And then we head to Venus. Now, Venus doesn't have many big asteroid-impact or impact craters, and they're not very old compared to the rest of the solar system. However, they think they've found one that breaks the mold. Certainly broke Venus. We'll talk all about that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here he is, the man of the hour. It is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing?
I've noticed that in most of the recordings we do, I wear dark colours. So today I thought I'd wear a white shirt. It's actually one of my golf shirts because, believe it or not, before we recorded today, I went out and had 9 holes. And I was running so late because it was slow. I had to come straight in here to record. So I don't smell too good. And that has caused Judy to leave the building. So,
oh, really? Well,
lucky this isn't smell-o-vision.
Yes, it is. But it sort of harks back to what we were talking about a couple of weeks ago about maybe aliens will communicate by smell. So you might be sending out a signal to the alien world.
Well, they'll never come here if that's the case. They won't want to come. Yeah.
Looks very smart, Andrew. And you've caught me off guard because I very nearly wore a light-coloured shirt today, and then I thought, oh no, Andrew will be dressed in something dark. I'll just got the same old blue on it.
Well, look at that, Unfortunately, golf shirts that are white tend to show a lot of dirt, and that's why I've got the collar up, because all the dirt's just, it's horrible.
I can't see it, don't worry.
Plus, our golf course is a very dirty, dusty golf course compared to most of the lush ones you see on television, so... Yeah. But before we get on to the stories, Fred, I read something that I thought would interest you, given that we talk about this semi-regularly. But the week just gone, Russia achieved a record launch of satellites. They put 53 satellites into orbit in one launch the other day, which is a record for Russia. But what interested me about it was the payload wasn't just Russian satellites. I mean, they've got satellites for their own purposes. I think most of them were, including their news agency, TASS, I think it's called. So there were Russian satellites. There were Chinese satellites on there, which probably shouldn't come as any surprise. This one might surprise people, though. Iran, a couple of satellites for Iran. And they launched a couple of sats for Zimbabwe as well. But that just adds more satellites to the growing numbers in orbit around the planet.
The Russians still have, because they were contracted to OneWeb, which is one of the satellite constellation companies. It's actually owned, I think the principal shareholders are British, but other countries as well. And OneWeb originally contracted to the Russian Federation for launches with their Soyuz launch vehicles. And when the invasion, the 2022 invasion of Crimea of Ukraine took place, I can't remember which way around it was, but essentially because of the various boycotts and things of that sort, the Russians commandeered those 20 OneWeb spacecraft that they had all ready to go. They were going to launch 20 OneWeb satellites, but they've still got them. And OneWeb very quickly changed and went with SpaceX, in fact.
Yeah, gosh. Yeah, I wouldn't like to be a lawyer writing up contracts for all this kind of work, because
exactly.
It sounds like it's a pretty messy business.
The risks in it, yes, exactly.
Yeah. But that satellite, all those multiple satellite arrays that are starting to build up around the planet just get thicker and thicker, which it's, as we previously mentioned a week or two or three back, not a good thing for the environment either, not just people who want to look out into space. Speaking of looking out into space, well, this was actually a mission, the Hayabusa 2 mission to Ryugu about 4 years ago, when it retrieved some samples from the asteroid and brought them back, and they've been studying those. And a few weeks ago, we did talk about one of the things that Ryugu has now revealed in terms of planetary formation and maybe how life evolved on this planet. Now it's revealing more data on the origin of our outer solar system, and it sounds like it was all done with magnets, or was it blue tack? Magnets.
Yeah, it is an interesting story. This is quite complex, but you're absolutely right. It is more data coming back from the samples of the asteroid Ryugu, brought back, as you said, by Hayabusa 2 in 2020. And so what has happened, as well as the chemical analysis that you've just referred to that was done on the various grains of material from this mission, scientists have now done magnetic analyses. And there are basically, these have been done with some tiny grains of dust from Ryugu, only about 1 millimeter across, but they've been measured very accurately by a device called a magnetometer, which, as you might guess, measures magnetic field strength. And so they've essentially stuck this thing in a laboratory with a magnetometer, and these tiny grains have had their magnetic fields sampled. And the interesting bit is there's no sign of a preserved magnetic field in these samples, which is a surprise. I'll tell you why in a minute. I'm looking at phys.org, one of our favourite websites for this news, and I'm going to read a little paragraph from their article on this, which it explains it a lot more accurately than I could. The scientists determined that the samples held no clear sign of a preserved magnetic field. This suggests that either there was no nebula field present, and by that they mean the magnetic field of the nebula from which the solar system formed, and that was a cloud of gas and dust. It suggests that either there was no nebula field present in the outer solar system where the asteroid first formed, or the field was so weak that it was not recorded in the asteroid's grains. If the latter is the case, the team estimates that such a weak field would have been no more than 15 microtesla in intensity. Now, I think, as I understand it, and I really should check this, but I think that's about a quarter of the Earth's magnetic field. So there's a bit more to say, though. So the Ryugu samples didn't really have any magnetic field. And that's a surprise, because we believe that nebula probably would have had a magnetic field. So another paragraph, if I may, the researchers also re-examined data from previously studied meteorites. They specifically looked at ungrouped carbonaceous chondrites, which are meteorites that have properties that are characteristic of having formed in the outer solar system. Scientists had estimated the samples were not old enough to have formed before the solar nebula disappeared. Now, the solar nebula is the cocoon in which the solar system was born, and it was eventually blown away by winds from the sun when it went through a windy phase. So it says any magnetic field record that the samples contained then would not reflect the nebula field. But the team decided to take a closer look. We reanalyzed the ages of these samples and found they are closer to the start of the solar system than previously thought. We think these samples formed in this distant outer region, and one of those samples actually does have a positive field detection of about 5 microtesla, which is consistent with that upper limit of 15 microtesla they spoke about before. So what they're suggesting is that the outer solar system, way beyond the orbit of Jupiter, probably beyond the orbit of Neptune, had a very weak magnetic field, but was still strong enough that material from the very limits of the solar nebula were pulled in and perhaps formed things like Uranus, Neptune, some of the smaller bodies, the trans-Neptunian objects. And a comment from one of the authors of this paper, and I haven't really credited who they are, but they are a group of scientists in a number of different universities, led actually by a postdoctoral researcher at Cambridge University in the UK. So they go on to say, when you're further from the sun, a weak magnetic field goes a long way. It was predicted that it doesn't need to be that strong out there, and that's what we're seeing. But still, it's a real thing. The magnetic field is real, but it was predicted to be weak, and that's what they're seeing with the evidence that they're getting from these Ryugu samples and some earlier meteorites that have been delivered to us from space, probably via an asteroid a few million years ago.
So 15 microtesla, which is only 30% of our own magnetic field today, which is 50 microtesla. So that's not a big number from what you say.
Yes, that's right. It's not a big number. I mean, I've always thought the Earth's magnetic field was quite healthy, but it's when you compare it with some of the magnetism that's used in industry or in scientific research, it's pretty weak.
Yeah, well,
there is a footnote.
You have to recharge a Tesla halfway to Sydney,
especially if it's a micro Tesla. So one footnote to this story is that this same team are going to look at samples from the asteroid Bennu, which has also had samples returned to Earth, this time by NASA's OSIRIS-REx, not OSIRIS-ROX, but the OSIRIS-REx spacecraft, came back to Earth in September last year. So it would be really interesting to see what results they get from that, if they do get a hold on some of these samples from Bennu.
Indeed. You did say something that I picked up on, and I thought it was worth revisiting. You said how the nebula that created our solar system was ultimately blown away by the sun, or the sun's solar winds, whatever. So even at the very beginning, we were destroying our creator, by the sound.
Yes, that's right. Blowing it away, that's right. We know that stars form in gas clouds of gas and dust. We see it, when you look at the pillars of creation, that's what you're actually seeing, pillars of dust with star formation taking place at the middle. And we know that very early on in the life history of a star, it goes through a phase which is known as the T-Tauri phase. T-Tauri is the name of a variable star, and it's the sort of, basically the prototype of this type of activity. And when they're going through the T-Tauri phase, they're sort of blowing away the rest of the debris. And we see that too. The Pleiades star cluster, which we see as the Seven Sisters in the sky, in our summer sky here in Australia. They are, when you look at them with a big telescope, or even with a small telescope these days, with the modern detectors that we have, you can see they're surrounded by a sort of blue shell. There's a lot of blue material in them. And that blue is the reflection of light from dust. It's actually why it's the same thing that makes smoke look blue. When sunlight falls on it, it's a process called Rayleigh scattering, which scatters the blue light preferentially. And so we see all this blue, dusty stuff, which is surrounding the Pleiades. Now, we think the Pleiades are only about 10 million years old. They're a young star cluster. So those stars have just gone through their T-Tauri phase. And what we see is, the last remnants of that dust cloud, the cloud of gas and dust in which they were born. So it's blown all the debris away. And the sun must have done the same thing as well. Probably not long after its formation, 4.6 billion years ago.
Yeah, it's just gone, hey, I'm here now. Rack off. So
just sweeping up the debris, really.
Yeah, cleaning up after itself, maybe. Yes, and it's exciting that we're getting so much data from such a small sample from the Ryugu asteroid, and there'll be more to come, I do not doubt. If you'd like to read up on that story, phys.org, as Fred said, or you can read the whole thing, lock, stock and barrel, with the 5 million people who signed the report in the journal AGU Advances. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and skiing was a go.
Space Nuts.
Now, to a story that we have done a couple of times, and that was the demise of the Arecibo Observatory in Puerto Rico. I know it's one of
that's right.
Yeah, I knew it was one of the Ricos, Puerto Rico. This was a really sad one because this is a famous one for all sorts of reasons. It's the one that's sort of nestled into a mountaintop, and they've used it in movies. It was used in the Jodie Foster film Contact. And it's just it used to be a very favorite place of cinematographers, but also astronomers, and it achieved a lot in its time, the Arecibo Observatory. But then a few years ago, it collapsed rather dramatically, and they have been looking into the reasons why. And now it appears they have discovered the cause and effect, and it's a bit of a sad miss by the sound of it.
It is, that's right. You're quite right, Andrew. It's got a very, very distinguished history, this instrument. Built in 1963. It was originally for what's called ionospheric research, kind of looking up at the atmosphere and measuring the radiation from it. But it was taken over in 1967 by the National Science Foundation for the astronomy community, and did all kinds of really interesting things. Actually, NASA shared the costs of maintenance and upgrades and things of that sort. Lots of discoveries, don't really have time to talk about them now, but one of them was a Nobel Prize-winning discovery, the binary pulsar, discovered in 1974. The issue, I guess, took most of us in the astronomical community by surprise when the demolition happened, but it sort of was an accident, not quite an accident waiting to happen, but there had been weakening of the structure over a period before that. It was 2020 when the thing finally collapsed, but apparently the failure of the structure actually began 3 years before that. In 2017, there was a Hurricane Maria, which went through Puerto Rico on September the 20th, 2017. And, that bombarded the area with winds that were in the region of 160, 170, maybe a bit more kilometers per hour, rather more than 100 miles per hour. And that was, something that hammered the structure. But the review that was carried out after that, there were inspections that were done in detail, and the conclusion of those inspections was that no significant damage had jeopardized the Arecibo telescope's structural integrity. Some of the issues were suggested to need repairs, but there were other things that caused those repairs to be delayed. And even so, they thought that this was not going to be an issue. And actually, the components that were going to be repaired weren't the ones that failed when the collapse actually happened.
That's a pretty significant point. Even though they didn't fix certain things, even if they had,
it would still have.
They weren't the problem. Yeah.
Yes, that's right. And then in August and November 2020, there were 2 cables that failed, and that basically was the thing that said, look, we've got a problem here. We think that the telescope is not recoverable from these cable failures. And they were going to decommission the telescope and then have what they called a controlled demolition to avoid the catastrophe. So that was all sort of in train towards the end of, in November 2020. There was August and November when those two cables failed. But then on the 1st of December, there was a failure of more of these cables, and that's when the catastrophe happened. The instrument platform collapsed into the dish, took off the tops of the support towers and damaged some of the observatory's other buildings. It was really a catastrophic end that probably people had in the back of their mind already, but they were working towards trying to avoid it. And it seems that some of the fractures were caused by zinc decay in the sockets that held these cables, what are called the spelter sockets. So zinc decay in those sockets that really led to the fracturing. That wasn't identified as an issue after the hurricane inspection. So they would, as you've just said, they would never have picked out what was going to eventually cause the collapse.
Yeah.
So yes,
from what I read, the capacity to actually identify the problem was nearly impossible. It was an invisible issue.
Yes, I think that's correct. So you can't. That's right. You can't really blame the engineers. The failures were in parts of the structure that weren't available for inspection, like the innards of it and things that really you would expect to last forever, but they didn't.
Yeah, that's very sad, and such an iconic piece of infrastructure, which I'm sure most people would recognize as soon as they saw a photo of Arecibo.
Yes.
It was so popular, just because of the way it was built and the way it was used, and it's some of its great achievements, as you mentioned, Fred. But it was a bit of a slow death. I mean, it was really probably beyond salvage before they identified that there was a problem, by the sound of it.
I think that's correct. That's a correct analysis, yeah. And of course, now we have the Chinese FAST telescope, the 500-meter aperture spherical telescope. That's sort of dwarfs Arecibo, actually. Arecibo was 305 meters in diameter. It was 1,000 feet. The FAST is 0.5 kilometer in diameter. That's a very, very big dish indeed.
Yeah.
Similar sort of structure, though.
Indeed, yes. And if people are interested, they did actually film that final collapse. It was they just happened to have a drone flying over Arecibo at the time, and they got footage of the collapse. So you can actually see it on YouTube if you're interested. It's pretty sad to watch. To be honest, I have seen it myself. It's such a wonderful piece of kit, as Fred would say, but all gone now. Are they going to? I suppose they're going to have to clean it up, or they've already probably done that, or are starting to do that.
That's right. That's a work in progress. But we do believe, from statements made by the National Science Foundation, that it'll be turned into an education centre, specifically to carry on. As a research centre for STEM. How can you best teach science, technology, engineering and mathematics? How can you teach that to young students? This will be what it will be doing. So it'll have an enduring legacy, as Universe Today describes it.
Yeah, it's hardly surprising when you look at Hurricane Maria, because in our language, winds of up to 200 kilometres an hour, most large structures would struggle with that. Yeah. And especially something that was built in the 60s, when they didn't have the kind of technology to reinforce big structures like they do today. So, yeah, very, very sad indeed. That's a story also on phys.org.
3, 2, 1.
Space nuts.
Fred, to our final story today, and we head to Venus, one of the more mysterious planets in our solar system, simply because we can't see it beyond its atmosphere, but we can use radar to map its surface, which has been done very effectively. One of the things that's fascinating about Venus is that its craters are much smaller and much younger than most of the craters found elsewhere in the solar system. But now they think they've found one that's probably the oldest and most definitely the biggest to be discovered at this point in time. But what's really weird about it is that it resembles impact craters on ice moons further out in the solar system, which I guess got people scratching their heads, and they've tried to figure out why, and it looks like they might have.
Yeah, that's right. It is a fascinating story, and it's almost one of these accidental discoveries that astrophysics is so full of. So it's radar data that you're always looking at when you're talking about the surface of Venus. I remember the Magellan spacecraft, I think I'm giving it the right name, was the one that gave us the best radar maps of the surface of Venus. And some of the features that came from those radar maps are similar to what we find on Earth. There's mountains. There's things that look as though they're definitely volcanic cones, but there are also what we call longitudinal structures, which are called tesserae. And these, I suppose, we use the word tessellated, meaning things that are rectangular in shape. And these tesserae are basically, if you imagine a radar map, they're more or less straight lines on the radar map, all going in the same direction, and they're caused by high levels of disruption geologically in the surface, and then they're thought to be at least 1.5 billion years old. So they go for a long way. They cover hundreds to thousands of kilometers, and probably up to 10% of the planet is actually covered with these things. However, there's a group of scientists who were looking at these tesserae in detail, and they noticed that some of them were going the other way. They were sort of at right angles to the main ones. And when they looked more closely, they found that actually they weren't straight lines at right angles to the tesserae. They were forming a curved shape. They had a curvature to them, and they were concentric. They're described as beautiful concentric structures that were very different from the rest of the tesserae. That's one of the researchers. And a lovely quote here: when nature gives you patterns like that, which are so obvious, they have a story to tell. I like that very much.
Yeah.
So that's suggesting when you've got something that's circular, and these stripes are circular, it's not a complete circle, but they're concentric. That's to say they have a distinctive center. What you're thinking about is an impact crater. And so this is a quote from one of the scientists working on this, some of whom are from Spanish University. If the structure... Actually, I'm not quoting here. I think I'm quoting from Sky and Telescope magazine, which is where this article is. If the structure was an impact crater, then it would be more than 5 times the size of the next largest one known on Venus. A size that fits well with massive impactors flying around the young solar system. But it's different. That's the thing. It's quite different from the normal impact structures that we see. It's got these concentric rings. And there's nothing like that on the moon. There's nothing like that on Mercury. There's nothing like that on Mars. But as you said, they did find exactly similar structures on 2 very different worlds. One is Callisto. It's one of Jupiter's moons, and the other is Europa, one of the other moons of Jupiter. And these are ice worlds, exactly as you've said. They're worlds with an icy covering overlaying a global ocean, which itself overlays a rocky core. And that's really weird because Venus is not an ice world.
No, it's not.
It's quite the opposite. But what it suggests is that there may have been a time in Venus's past when it had a similar structure to the ice world. So, as I said, ice worlds are a layer of ice with water underneath. If you think of
let me guess.
Go for it.
The floor is lava.
Yeah. So if you imagine a lava crust, a thin lava crust, overlaying molten lava, then you've got a similar structure, a solid layer on top of a liquid. And so this is exactly the same effect. This is basically what led this team of researchers to model what would happen if you had an object hitting a solid crust covering lava, either a lava ocean or lava pools. And apparently what they found, and this is again quoting from Sky and Telescope, the team found that a single large object hitting a hard 6 kilometer thin crust could melt the underlying layer, splashing chunks of solidified scum to make the tessera. But a single impact couldn't simultaneously make the ring structure. And so they're now postulating basically an initial impact that produced that straight line crinkling that I mentioned, the tesserae, but then another one. So that what that leaves is a thin crust over a pool or an ocean of hot lava, and then the next one, a next impact, while that pond is still fluid, another object hits, shatters the crust again, and that's when you get the curved impact structure, the stuff that we see similarly on Europa and Callisto. So really quite an extraordinary bit of research, but it may well be that they've pinpointed exactly what happened to the early Venus, because we know that in the early history of the solar system, it was it was a hellish place. There was debris charging around all over the place, bits of unbuilt planets and asteroids and all the rest of it. So impacts were very high. What we call the late heavy bombardment.
Indeed. And I suppose now, Fred, if it's confirmed that this is a major impact crater, they'll have to give it a name. The one on Callisto's got a great name. It's called Valhalla Crater.
Yes.
So they would surely have to name this, wouldn't they?
I think it will get a name. Yes, that's right. Yeah. Once again, the names of everything have to be ratified by the International Astronomical Union. But I think the suggestion would come from the authors of this paper as to what it might be. I think the lead author is Vicky Hansen from the Planetary Science Institute. So they're probably thinking now about what this could be called.
Yes, it's quite a discovery and great technology, given we can't see the surface with the naked eye.
Yes, isn't that amazing?
That's right. Big pickup indeed, yeah. You can read that story, Fred mentioned it, skyandtelescope.org. We're all done. Thank you for your company. Don't forget to visit our website. And if you listen to us through whatever platform, please leave a review. We value the reviews because they help to get the word out and bring more people on board. And it's good to see lots of newbies following Space Nuts who've messaged us in recent months to say, hey, we knew, we found you, we started at the beginning, we'll catch up soon. You've only got 470 to go. That sounds me, that number of episodes. It does. I know we started doubling up not long ago, but it's still good numbers. Thank you, Fred, as always. You are a delight to speak with, so I'm told.
Thanks, Andrew. So are you. So I'm told. Speak to you soon. Thanks again.
All right. See ya. Fred Watson, astronomer at large, and someone else who's a delight to talk to whenever he turns up, and it wasn't today, is Hugh in the studio. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.